interplay between PDE and Hamiltonian dynamics. I mean, I'll make it clearer. And roughly speaking, there are going to be more objects coming in. But for now, the three sort of major and main objects going to be, the first object is really, we talk about it, is about the Lagrangian dynamics. That comes from the Euler-Lagrange equations of the minimizer. So this is for gamma and gamma dot. And its equation is going to be d over dt of dvl gamma gamma dot equals dxl of gamma gamma dot. So that's our first object. Then, in the previous few chapters, we also have been talking about its relations to the second object, which is about the Hamiltonian system. And, this is a system of ODEs for 2n equations that you have. I should have said that the unknowns are x and p. And again, x is gamma, right? P is a generalized momentum. And you have a system that says that you have x dot equals to dph of xp, and p dot equals minus dxh of xp. So that's our second object. And again, if there is no PDE, then it would just about sort of the ODE systems. And surely there are certain study earlier in the past about those, and the modern viewpoint is that surely we can connect them to this the PDE, so both of them are closely related to the third one, which is the new object that we introduced in this chapter, and this is about a stationary Hamilton-Jacobi equations. Jacobi PDE. And here, I have C is essentially the energy level, the fixed energy level. And our PD is that I have H of X dux equals to C in the torus, which is Rn mod Cn. And that's our third object. And the main goal of this chapter is about discussing the relation between the three objects. And, there are going to be more objects coming in with also the time-dependent Hamilton-Jacobi equation and stuff like that. But for now, those are the three main ones. And then we're going to try to study more about their connections and also some further hidden points. Okay, so that's sort of the sort of the brief overview of the objects that we discussed in the previous lecture, and more precisely, I recall here on the lab panel the main theorem we proved last time is that if we assume that U is a C2 function that satisfies the Hamilton-Jacobi equations, and as we said, C2 is a bit too much, right? Because if U is C1, we can still make sense of the equations in a very classical way. And we say that if that is the case, and if you start your Hamiltonian flow with the vector x, x naught du x naught, so if your Hamiltonian flow start at the point x naught p naught, which is x naught du x naught, then you run your Hamiltonian up to sometime xt pt for the time t, then this is nothing but xt du x. Okay, so that's pretty cool because it tells us that the du preserves the structure of the generalized momentum p, and in particular we have that the graph gamma, the graph of the gradient, is invariant under the Hamiltonian flow, and that was our main theorem last time. The proof is not too complicated, but it's really beautiful, and worthwhile remembering it. And for today, we want to discuss further, right? Again, at least from the from the theoretical viewpoint. Again, you might say that, C2, C1, they're the same and stuff like that, which is, more or less true in certain settings if you have regularity. But in this case, turns out that later on, we don't have a lot of regularities of the solutions. So, we say that U is C2 is too strong. So we want to, say that, okay, let's just require, this is not. So let's just weaken the regularity assumption. Let's just assume that U is C1. And this is enough, right? Because our equation is a first order equation. So U in C1 is a solution to the Hamilton-Jacob equation h of x du equals to C in Tn. And this is still a classical solution. Okay, here by classical, I meant that, you differentiate the U, you have the still continuous functions and you plug in here. It makes a total sense in a classical way, everything is defined everywhere, okay? Then the question is that our main question then is still, do we have the invariance property? Invariant property that we have phi t of h of gamma of the graph of du is still in gamma. Okay, so that's the question that I want to answer. Again, at least just theoretically, it might not be, it might not be, like really striking, but it's sort of like the first simple way to try to approach the problem, and it turns out that the answer is yes. And as I said, we're gonna need some preparations to prove it. So today is gonna be certain preparations, and we're gonna prove it next time. Again, I'm going slowly in this first part of the new chapter because I want to make sure that we are, not lost in details. And the following is an important theorem. So this theorem, it's going to be a again a short way to say about this theorem is that this theorem here is sort of an equivalent characterization of C1 subsolution. Okay. So that is a shortcut way to describe the theorem, and I'll explain what do we mean, and then by the end of the lecture today, I'm hopeful that we have a bit of time that I can explain to you that actually the assumptions here can be relaxed. Okay, but let's do the classical one first. So we have C1 functions. So U is C1, and we say that the two claims I and 2I are equivalent. And the first claims is about h of x du is less than or equal to C. So, it's just a matter of definition. So if we have h of x du is less than or equal to C with U is C1, with U in C1, then we say that U is a C1 subsolution to the above PDE, okay? So sub here just because, it's less than, right? And it's C1, everything is nice. So the first claim is about that U is a subsolution, and similarly it's greater than or equals to, it's about super solution, okay? And the second claim is totally different. The second claim doesn't see much about the you know, the gradient or anything structure, but the second point is about, you know, the action functional, right? It's about that if you have any curve gamma absolutely continuous, or you can, you know, make it C1, that doesn't matter because we can do approximations. So if you take any curve gamma, then the action functional on the right is going to be action functional of gamma. I mean, with C is there because you know, it's a normalization, the equation has C, so it has to be there. It's going to be greater than or equals to U evaluated at the two endpoints. So so the first point is about that. The second point is, you know, you can say that U of gamma B minus U of gamma A is less than or equals to the action functional of gamma plus the value C, you know, taking the difference of the interval of integrations, right? So it's different because, oops, I don't know, okay. Nothing happens, okay. So I have, this is gamma I, this is gamma B. And, you know, you take any curve gamma connecting the 2 points, then we are saying that the values at the 2 endpoints here of U is always less than or equals to the action function of I on gamma plus C times B minus I. And I should say that it's a remark. So this theorem alone plays an essential role in the whole context of Wickham theory. Okay, why is it important? You know, one of the points that this is important is that, you know, the first claim is about, you know, this first claim is about, this is a PD claim, right? That's the first claim. It's really about a sub-solution to a PDE. The second claim is already about the Lagrangian viewpoint, right? So it's about the Lagrangian viewpoint already, and the two claims are equivalent. It's not yet clear, but it essentially allows us to, you know, connect the dots between, you know, PD and Lagrangian viewpoint. Okay. The proof is actually not too complicated, as you can see. And as I promised, we're going to use the duality inequality almost every lecture. Okay. Again, do correct me, you know, point out to me which lecture eventually that we didn't use this inequality. Anyway, so let's prove it. So the first claim is going to prove I implies to I. And again, stop me if you have concerns or questions or anything you want to discuss. As always, to evaluate the difference of the value of U at the two endpoints. And again, you know, we are using the fact here that because U is C1, right? U is C1. And, you know, gamma is absolutely continuous is fine. Or again, by approximation, you can consider gamma to be C1, piecewise C1, or piecewise C infinity. Those are okay as well. So you evaluate it and you just use the fundamental theorem in calculus. You see that, you know, it's just du of gamma dot with gamma dot ds, right? And again, we are using the fundamental, important inequality in duality theory. We are saying that du dot with gamma dot is less than or equals to h of gamma du plus L of gamma gamma dot, you know, so, and let me emphasize here. So in particular, the most often used inequality is going to be that du of gamma s gamma dot s is going to be less than or equals to h of gamma s du of gamma s plus L of gamma s gamma dot s. Okay. So we are using that. And again, everything here is a classical form. everything is smooth enough, C1 continuous, so that every evaluation is in the classical way. And you see that in particular here, we are using the fact that H is a, sorry, U is a subsolution, right? So H of gamma du is less than equal to C. That's why C, the normalization comes in. And the Lagrangian is just the Lagrangian, right? So I just kept it. I'm not doing anything to it. And you see that this is exactly the action functional, I mean, normalized by C, if you have to talk about it. So, again, it's simple, but yet very beautiful. Surely I want to make a quick remark here before we move on, is that remark that, we said about it, but U in C1 was used to compute d over ds of U gamma s, right? By the chain rule, we were using that to compute the derivative in the s variable. So at the end of the lecture, I would like to discuss that, in fact, let me use a different color. In fact, we can still obtain the result if U is only Lipschitz. Okay, and this is a big deal. I mean, it's gonna be allowing us to relax the assumption a lot, because we only require the Lipschitz assumption. I'll come back to this by the end of the lecture. And it turns out that the Lipschitz assumption is it's the most natural one, and it's the practical ones that we can expect. Not not better than Lipschitz. Okay, in the general setting. Okay, so that's that. Now let's do the point, the converse. So 2i implies I. So for this, we are using a little bit of the trick here. So what's the general philosophy here? So the general philosophy here is, you're going from the action functional, because 2i is about the action functional, right? And you need to go back to certain PDE. And in order to do so, you would need to see, du x occur, right? And once you can find a way to, once you can find a way to evaluate du, then, or any terms involving du, or the PD involving du, then you would be able to connect the dots. And this is a general trick or general framework that also occurs not just here, but also in optimal control or dynamic programming principle, if you have heard about those. The point of making du occurs is that, if this is the point x, we would need to see that, like what's going to be it's, let's say that, so to see du x, I would probably need to see the directional derivative of u in all the directions, all the possible directions, right? I mean, not always, because there could be better ways in certain cases, but at least it's natural to see what's going to be du x dot with v, right? Where v is a vector, or I mean, you can write this one to be del u over del v of x, which is, just the directional derivative in v, which is drawn here on the left panel. Okay, and to do so, to see the directional derivative in v, then it's a natural way to bring into observation your part gamma, the part gamma is nothing but just a straight line segment going in the direction v, right? Because that allows you to observe what's going to be dux dot v, which is again the directional derivative in the v directions, and that's sort of the trick, or I mean the general observations for just differentiability of multivariable calculus, right? Okay, so so we are doing so. So what you're taking into account is that gamma is just the line segment connecting x to x plus tv, and then we're gonna let t goes to 0 eventually to see the directional derivative, and that's sort of the idea. Okay, and let's just write it down. So I have, this is the gamma s, and t is just a positive number to be you know, allowed to go to 0. And if you do it that way, then you consider this is to be the part, then you have that u of x plus tv minus u of x is nothing but u, the difference of u evaluated at the two endpoints, right? X plus tv and x. And by the second property allows you to see that this is less than the action functional plus the normalized constant c times t. And the action functional can be written down explicitly, right? You know, again, you have gamma s is x plus sv, right? For 0 less than equals to s less than equals to t. So the action functional L of gamma s, gamma dot s ds, you know, you just write it down, right? This is integral from 0 to t, L of x plus sv, and its velocity of the curve, I mean, its velocity is just v, right? ds, okay? And you see that, okay, I mean, for t small, so if t is near 0, then again, I mean, L is nice and smooth, so you see L of x plus sv, v is essentially L of xv, right? I mean, there's certain small difference, but I mean, that is negligible when t gets to 0. Okay, so so that's exactly the point that we are doing, right? We are evaluating the directional derivative of u at x in v, in the direction v, and you just write out the definition. And from the definitions here, you are dividing, it's less than equals to the right hand side, and the right hand side you are dividing everything by t. So you have 1 over t times this integral plus c. And you know, I'm doing it, okay, maybe I'm just gonna write this time, and then next time we can just you know, take this for granted. You can prove this one by 10 different ways, I guess. So you know, one way to prove this one, the s plus c, probably one of the easiest way to prove this one is just use the mean value theorem, right? You're taking the average 1 over t of the integral from 0 to t, so this is equals to L of x plus s of t, v plus c for some s of t between 0 and t, right? And then you have limit as t goes to 0 of L of x plus s of t, v is just L of x v, right? So that's why I have the limit as t goes to 0 going to be L of xv plus the constant c. Okay, so that allows us to conclude a very important yet very beautiful viewpoint. No, a viewpoint, very important yet beautiful and simple point, that is dux dot with v minus Lxv is less than or equal to c. Okay, and now you can maximize over all possible vector v in Rn. You know, the left hand side is always less than or equals to c for any v, right? So you take maximum over all v, that gives you the Hamiltonian, and and this is less than or equal to c, then we are done, right? So another remark I want to make here is that this is a general idea to go from either action functional, so action functional, or you can see that in the PD framework, sometimes in optimal control, people say that this is dynamic programming principle. Or dynamic programming principle. To PDE. Okay. This is a very general way. Of course, I mean, for different problems, you might have to be quite flexible in what you're writing down, but overall, it is the way that it goes. Okay, so we're gonna use this one also later on, but I'm hopeful that this proof is simple enough. You see that the overall idea is really beautiful, yet not too complex. And again, later on, we're gonna generalize this one to the most general version, which is also the most realistic one that is applicable for this case. Okay. And you see that from the second viewpoint, the second point was about so I'm putting a red box here on the left panel. The second one is really about an identity involving the left hand side is a difference of u, evaluating at the two endpoints, and the right hand side is an action functional of the curve gamma. And you see that there is nowhere that we would need to require that u is C1, right? The left-hand side makes total sense for any function u. And in fact, we only need to require, in this definition, this is called dominated function. So I'm trying to respect Fatih notions, so that sometimes the notions in dynamical system community is very different from the notion from PD framework. I'm trying to, because this is a dynamical system course, so I'm trying to keep the notions in dynamics, and sometimes I'm going to try also to bring up the PD notions and bridge them together. So they call it dominated function here. So they say that u in so what is remarkable in this definition is that in the definition we only require that u is in the set of continuous function and no requirement on differentiability of u. Okay. Even with that, we can still make a total sense of the definition. So we say that u is dominated by the action, dominated by the Lagrangian L plus C. Again, C here occurs just because it's a normalized constant. It's really the fixed energy level. It's a normalized constant. And we denote it by u is curly less than or equals to L plus C. U is, you can just define whatever you want, right? It's just a relation. If for any continuous piecewise C1 curve gamma, you have the actions is always greater than the difference of u evaluated at the two endpoints, and also that it's a weird notion to me, but so Fatih wrote it to be DC of Tn. It's all you collect all the possible function u continuous, so that U is less than equals, not less, U is dominated by L plus C. Okay, just a matter of definition. And I said here that, again, piecewise C1 curve can be replaced by C infinity or absolutely continuous curve. You can do all those by definition. Sorry, by approximations. Okay. Right. So again, our major goal here is that we're gonna show in the next lecture is that if you see one, then the graph of the gradient is still invariance under the Hamiltonian flow. I kept repeating this because, again, I'm trying to make you get used to this thing and you think that it's natural. Okay. All right. So before doing so, I need some preparation here. So what I'm going to do now is that I'm going to do the preparations and then see if we have discussion, interactive discussion or anything. And then I'll try to give you the proof, one-way proof that, instead of requiring you to be C1, requiring you to be Lipschitz is good enough. And I'll tell you why Lipschitz, why not something weaker, okay? But before that, I need this discussion to be used next time. So the discussion here is about on the left panel is about what is about we were talking about invariance under the Hamiltonian flow, right? And this is about the invariance property. And the invariance, we were just talking about invariance under the Hamiltonian flow. And the point here is sort of how to relate, the invariance under the Hamiltonian flow with the invariance under the Lagrangian flow. And it turns out that surely we can link them, right? Because earlier we already talked about how to go from Lagrangian to Hamiltonian and vice versa. And this is exactly the same way. But again, I want to remind you so that, things are not getting lost. So you define these curly L functions. Again, it could be a little bit confusing, but curly L is not the Lagrangian L, right? L is just the capital L. Curly L is the map from Tn cross Rn to Tn cross Rn. So you take xp, you map it to Lxv, which is xp, right? And p is dv of L. Okay, so I kept saying that, but let me say it again. Okay, maybe let me reverse the order so that I'm on the same page here. This is Vt of L, Vt of H. So you start with xv here, and you linked it to xp, right? And this map is the curly L map. No, it's just one way. You go from xv to xp, then this is the curly map L. And P is nothing but dv of Lxv. Okay, that's the map curly L. And we have shown that curly L and curly L tilde ck minus 1 diffeomorphism, right? And curly L tilde is just the way that you go back, right? And here, if you go from xp back to xv, then this is curly L tilde, right? Am I writing? Okay, fine. And curly L tilde, then if you go back, then what you should have is that you should have V is dph of xp. Okay, and that's the way to get back. Okay, and in particular, if you have the gradient, right? If you're x dux, then you can write to be L curly L tilde of x dph of dux, right? Again, just dph of x p. Okay. And since you have the point, last time we talked about that, right? To go from the Hamiltonian flow to Lagrangian flow, then you have just take the L, compose with VTL, compose with curly L tilde, then you have that, right? So of course you can go back, right? You can go in the converse way that you take curly L tilde, compose with VTH, compose with curly L to have VTL, right? So by that, again, nothing is new here. I'm just repeating myself. But what I'm saying here, what is important here is that, you know, you can either prove that the graph gamma that is invariance under, so what is important here is that to prove gamma that is invariance under the Hamiltonian flow, right? So invariance here means this, then this is equivalent to prove that you take 50L of gamma tilde is invariance under the Lagrangian flow, where gamma tilde here is nothing but just x dph of x dux for x in the torus, right? And again, I mean, if you think about this, you can again think about it as a you know, as a generalized momentum. Okay, so that is your gamma tilde, and you just need to prove that you know, you just need to prove that your gamma tilde is invariance under the Lagrangian flow, and this is going to be the tool that we are using to prove the invariance property when U is only C1, and you can guess why, right? Because if you come back here, you know, to prove this result, you see that we already have the important properties earlier about the theorem, right? We can go from the PDE to the Lagrangian framework. So here it's natural to use the Lagrangian framework, and this is why, you know, why here to prove this result is it's natural to use the Lagrangian framework, that you have phi t of L gamma tilde is subset of gamma tilde, right? And that's what we're gonna do. And hopefully I'm not mistaken. I'm gonna need to check and stuff like that, but that's the way it goes. Okay. So of course, as I promised, we can discuss this point. Let me just write down, and then I stop first if we have discussions, and then, you know, if there's none, then we're gonna go on. So so a generalized, oops, point. Okay, so I'm gonna write I tilde here is I tilde is real, fine, whatever. Is that I have U is a Lipschitz function. So Lipschitz function by Rademacher theorem, then it's differentiable almost everywhere, right? And I have that h of x dux is gonna be less than or equal to c almost everywhere. In the torus, then still that have I tilde implies 2i. Okay. All right. So that's what I'm going to prove. And in fact, the converse also holds, but you know, let's keep it for later. So let me stop here a little bit, and I'm calling for discussions. Anything you want to chat with me or with your peers before we move on to prove this last point. Again, today's Friday, we can take it easy, but if you have something to discuss, anything of your concerns, or, you know. No? Okay. All right, so if there is none, you know, again, there is, of course, I mean, the lecture is quite interesting, but you know, quite simple today, right? So so surely that again, do let me know if there are some points of your concerns, and do let me know if I'm sort of doing it in a weird way that making you feel lost. And eventually the picture is still about linking the three objects between the PDE, right? And then Lagrangian flow and the Hamiltonian ODEs. Okay, so let me discuss this one quickly with you, and then again, it's Friday, so we can take it easy, although it might take me longer. Okay, so so let's look at this PD first. Okay, now if you think about it, you have okay, so first look at the PD h of x du x is less than or equal to c. Okay, now if you think about this one for a long time, not necessarily right away, that you see that h is superlinear in p, right? So you see that if p goes to infinity, the length of p goes to infinity, you would have h of xp goes to infinity, right? So clearly, again, assuming that everything is nice, you have p is the gradient of u here. H of xp is bounded by a constant, implies that p is bounded by a constant, right? So, so clearly, when h of x du x bounded by a constant, then again, if everything is nice by a priori estimates, you can imply that du is bounded by a constant, right? So this is important because when we say that du is bounded by a constant, then we say that naturally it's nice, and it's just natural to require. So it's natural to require u is Lipschitz, right? It's natural. Requiring u is Lipschitz is natural, right? And it turns out that this is exactly the case. We say that H is superlinear. Later on, you can see that we're gonna relax it to that H is only coercive, which is fine. So you see what I meant here is that it's very natural to require that U is Lipschitz. C1, who knows, but U is Lipschitz is fine. We just need to require that. And what we claim is that although the only U is Lipschitz, and this one is only defined almost everywhere, right? You can imagine that your function U can go up and down like zigzag one, for example, U is like this. Then it's a nice zigzag function that is only defined everywhere except the corner points, right? So that's a Lipschitz function. But still, what is really remarkable is that we can still prove that, I tilde implies 2i. And this is a remarkable point that I want to prove to you now. At least sketchy, okay? So proof of I tilde implies 2i, okay? So the idea is very simple. U is not too smooth. Then, if you face something like that, then the idea is smooth it out, right? And there are various different ways to smooth out functions, and then the simplest way is to use convolution with a convolution with a standard kernel, right? With a standard multiplier. Okay. So you take a multiplier. Oops. Take a multiplier. I'm losing all my Greek characters now. C. Okay. Take a multiplier C. So C is compactly supported smooth in Rn. Taking non-negative value, say support of C is in the unit ball, if you wish. 1D picture, this is -1, 1 or something like that. And then for epsilon greater than 0, you rescale it, right? You define C epsilon x equals to 1 over epsilon to the power n, C of x over epsilon. Again, you rescale it like essentially, roughly speaking, like a bell curve, right? Whatever. You rescale it to be tighter but higher, C epsilon. Okay, surely that I should have said that the integral in Rn, you require that the integral in Rn Cx dx is 1, and this also implies that integral in Rn C epsilon of x dx is 1. Okay, so you take this one to be a standard multiplier. You define u epsilon of x is C epsilon convolute with u at x, just smooth it up, right? And this is integral in Rn of C epsilon x minus y uy dy. It's also integral in Rn C epsilon of y u of x minus y dy. Okay, and because this is, you know, in Rn, you can because the support is in the ball of radius epsilon, right? So this is also b of x epsilon C epsilon of x minus y uy dy. Okay, so that's the first step to smooth it up. The second step is that you realize that h of x du x is less than or equal to c almost everywhere, right? And you can just integrate it with respect to this multiplier. So you see that integral in Rn of h of x dux, oops, integrate with c of, no, let me change it to y so that I'm not having to change it many times. H of y duy of c epsilon of x minus y dy is less than or equal to c, right? Because again, h of this one is less than or equal to c, and this integral is 1, right? So everything is fine. And you see that this integral is just equals to the integral in the ball of center x radius epsilon h of y duy c epsilon of x minus y dy is less than or equal to c, right? Okay, so what I'm doing here is that I'm trying to just use approximations. I'm not very happy with this y, because y is running, right? Y is running here, here, and here, and dy. So too many y's, and I cannot control all of them. So the trick is that this y now, I'm going to fix it to be x. Okay, I'm going to fix it to be x. So what's the cost do I have to pay? So if I fix it to be x epsilon h of x duy c epsilon of x minus y dy, right? Well, because x and y are close to each other, they are nearby of order epsilon, right? So the cost I have to pay is just nothing but less than or equal to c plus c times epsilon, as you know, h of y p minus h of x p. P is bounded. It's less than or equals to c epsilon for y minus x is less than or equals to epsilon, right? Okay. So you see that I'm paying a certain price, but I can have the cost of having x fixed. Okay, then I'm more or less done now. Here I'm using the Zen inequality as p maps to h of xp is convex. Okay, Zen inequality says that if h is convex, then the convex combination in p of h is going to be greater than or equals to h of the convex combination, right? So the above integral is greater than or equals to integral inside h of integral inside duy c epsilon of x minus y dy. Okay, so really convexity plays a big role here. Without convexity, I'm doomed. Okay, but again, as I said, this means that h of x du epsilon of x is less than or equal to c plus c epsilon. Okay, and this is good as u epsilon is smooth, right? Okay, now I can use exactly the earlier theorem we proved, right? But for u epsilon, because we proved for u is c1, but in this case u epsilon is smooth. So you can see that from here you have u epsilon of gamma b minus u epsilon of gamma A less than equals to the action functional L of gamma S, gamma dot S ds plus C epsilon. I have to pay the price of C epsilon, right? Times B minus I. Okay, so this is amazing. We have that. Now you let epsilon go to 0. You're done. Okay. So that's pretty much it. So you see the whole framework was that you start with a function that is not smooth enough, and as a general trick or general strategy in analysis, PDE, you often have to smooth it up by certain technique, and what I'm using here is using the standard just convolution is a standard multiplier. I'm using convexity. I'm smoothing it up, and I see that u epsilon, a smooth version of u, still satisfy an approximated equations. So, and u epsilon is smooth, and I can use the theorem again, and I pass the limit to have it done. Okay. Any questions or concerns for me about this? Okay. All right. So if not, then I think we are done. And again, what we proved today, yes. Okay. Oh, okay. Good. So what we proved today, although it looks very simple, but it's a really remarkable point. And then once we have this week, we can go forward. So thanks a lot, and have a great weekend. Again, stay safe and healthy, but also like try to take some activities, not activities out in the nature or something like that. And okay, so see you on Monday next week, and have a great weekend.